Let's finish the discussion on parallel lines with a proof. Remember when I said that the addition of the three angles of a triangle measure 180 degrees? Let's prove it. We begin by saying that a circle has 360 degrees. It has 360 degrees because a hexagon, or a six-sided polygon, fits perfectly inside a circle, giving you six perfectly matched, congruent, equilateral triangles inside the hexagon, projecting six angles with 60 degrees each. 6 times 60 equals 360. We can find hexagons in nature, in flowers, and, of course, in a bee's honeycomb. Now, way back when humans decided it was time to learn how to read and write, the experts say in Mesopotamia, present-day Iraq, for some unknown reason, people decided to develop a numerical system to the base 60. In other words, instead of counting to the base 10, like we have now, where we repeat the same number every 10 by combining them differently, they repeated the numbers every 60 numbers, before the numeration started again. Eventually, societies dropped the base 60 and adopted the base 10, but the practice stayed with us to measure time and angles. Anyway, if arbitrarily a circle has 360 degrees and we take it as a given, then by slicing the circle in two, a half a circle has 180 degrees because 360 divided by 2 is 180. Here's where the proof starts. You place two parallel lines on a flat plane and cut the parallel lines with two transversals. But you do it in such a way that a triangle is formed. So we can have a triangle we need to prove that it is 180 degrees. Now, label each internal angle 1, 2, 3, 4, 5, 6, and 7. Because angle 1, 2, and 3 are part of a linear triple, then their addition must be 180 degrees because they are part of a line. Now take the transversal that cuts from top left to lower right and let's examine the angles it forms, disregarding of course what is happening with the other transversal. We can see here that angle 3 and angle 6 are equal. Why? Because if two parallel lines are cut by a transversal, then the alternate interior angles are equal. We said that in the last section. So angle 3 and angle 6 are equal. Now, going to the other transversal line, we see that the same thing is happening with angles 1 and 5. They are equal for the same reason. They are alternate interior angles formed by two parallel lines. Okay, so angle 3 is equal to angle 6, and angle 1 is equal to angle 5. At this point, we make our move. We substitute 6 with 3, and 5 with 1, because we say that they are equal, leaving us then with angles 1, 2, and 3 inside the triangle. Didn't we say previously that angle 1, 2, and 3 are up to 180 degrees because they are part of the same line? Well, these same angles are now inside the triangle. So the triangle also adds up to 180 degrees. In other words, triangles have 180 degrees because a straight angle, or lines, also have 180 degrees. Here's the formal proof. Like always, we start with two columns, one for the statements, another one for the reasons. The first statement is what we know so far. Two parallel lines cut by two transversals forming a triangle. The reason is of course given because it is the if part of the theorem. Now we continue by identifying the angles shown and realize that angles 1, 2, and 3 are part of the same line and therefore they add up to 180 degrees. So we say so in the statement and give us reason that that is the definition of a straight angle. We also state that we are working with a triangle, I must say so in step 3 by defining the triangle. Now we complete step 4 and 5 by deducing that if the lines are parallel, then the interior alternate angles must be equal. This happens twice. So angles 3 and 6 are equal, and so are angles 1 and 5. Okay, so now we have established 2 angles already. So for the last angles, we see that we are talking here about the same angle, which is equal to itself. It may sound silly to mention this, but every angle in the triangle must be accounted. Finally, we established the link between line and triangle by making the actual substitution and call angle 1 plus angle 2 plus angle 3 180 degrees. But now not as part of a straight angle, but as part of a triangle. There. Done. A formal proof.